This video introduces capacitors and inductors. Unlike resistors, which basically use energy, turning electrical energy into thermal energy, capacitors and inductors are storage devices. They actually store the energy. So we'll take a look at number one. We'll review the physics of resistors, and then we'll compare that or look at the physics of capacitors and inductors. And then we'll look at series and parallel connections of resistors and capacitors and inductors. And we'll save charging of capacitors and inductors for another video. So resistors, just remember that resistors oppose current flow, and they do that by turning electrical energy into thermal energy or heat. All right, the unit of resistance is ohms. Resistors also, if you were going to buy a resistor, you also have to consider the maximum power rating so that the resistor doesn't overheat and burn up and become destroyed. So when we, like I say, when we purchase a resistor, we're going to purchase a resistor based on, number one, what its actual resistance to current flow is, and number two, a power rating. So when we look at capacitors and inductors, we'll also have two values to consider. Resistance is determined by the physics of the element. There's the resistivity, which discusses the type of material and how easily current will pass through that type of material, times the length of the material divided by the cross-sectional area. So if the length of the resistive material gets longer, then the current's going to have to pass through more of it. That's going to increase the resistance. But if it has a larger cross-sectional area, it has more ways to pass through, and therefore the resistance will decrease. Alright, capacitors are made of two metal plates separated by a dielectric. Now, dielectric is kind of a fancy word for saying an insulator. So basically, a capacitor is two metal plates separated by some sort of insulation material. Okay, capacitors store energy. So they don't use the energy, but they can store it. So they store the energy within an electric field between the two plates. They do this by building up a positive charge on one plate and a negative charge on the other plate, and therefore the attraction between the positive and negative charge is actually what is that energy, and so the energy is effectively between those plates. All right, the unit of capacitance is farads with a capital F. Capacitors also have a maximum voltage rating. So when you're purchasing a capacitor, you need to know what the maximum voltage across those plates is going to be. And the reason for that is if the voltage is too high, it can actually jump through the dielectric, or basically burn a hole through the dielectric. So similar to resistors, we have two things we have to worry about when we're trying to purchase a capacitor. Number one is simply the capacitance in farads, but we also have to consider that voltage. lot of capacitors actually have a really small voltage, maybe 15 volts or 50 volts. So you have to take into account that voltage. Now, capacitance is determined by three aspects of the physics of the capacitor. So the one aspect is something called the permittivity, which we use the symbol epsilon for. That's a Greek symbol epsilon there. And that is the permittivity of the dielectric, basically specifies how much energy we can put within that electric field. The other aspects are the distance between the plates. So as the distance of the two plates gets smaller, the capacitance actually gets larger because they're closer together, they have a stronger attraction. And the area of the plates. The area of the plate is where we're putting the charge. So if it's a larger plate, we can put more charge on it, and so therefore also increase the capacitance. Now, capacitors, as I said before, they're storing energy. Technically, they're storing energy within those plates. Now, this is done by passing a current. Remember that current is the charge, which we usually represent in Q as Q divided by seconds. And so what we're going to do is we're going to move charge and store it onto those plates. Now, technically, current does not flow through the capacitor. What we basically do is take electrons off of one side and place them on the other side. So no current actually flows through a capacitor. It's simply a matter of moving charge through a circuit and returning it or putting it on the other side of the plates. So we can determine how much charge is on that if we know the capacitance, which again is defined by the size and makeup of the capacitor times the voltage. So if you look at this, it looks almost like Ohm's law, right? Well, Ohm's law, we had that the voltage is equal to the current times the voltage, but in this example here, we have that the charge is equal to the capacitance times the voltage. All right, so if the capacitor is not charged, so there's no charge on the capacitor, and you connect up a circuit to it, current is going to start flowing, because what we're going to do is we're going to start moving that current off of the one plate, or the electrons off of one plate and storing them on the other plate. So current will move through the circuit. Now again, it's not actually moving through the dielectric. No current's moving through the dielectric of the capacitor, but it would be moving through the rest of the circuit. And so we're simply taking the charge from one side of the capacitor and putting it on the other. So when you first hook up that voltage source, it actually, the capacitor almost looks like a short circuit, drawing a lot of current. This is one thing, like when we turn on our TVs or DVD players and things like that, there's always a current surge, and this is at least in part of that, the current surge is because these capacitors need charged up. Once they get charged, however, the capacitor acts like an open circuit and no DC current will flow. Okay, so no direct current will flow. Once it's charged, it's going to stay charged theoretically forever. Now, eventually some of the charge will leak off, but it'll take quite a long time if you have a very good dielectric. So if you charge up a capacitor and just disconnect it, that can actually be quite dangerous, because the charge is still on that capacitor if you never gave it away to discharge. And when you look at like the old CRT type TVs and things, they would have very large capacitors in them that could have charge on them. Power supplies are the same way. Power supplies will have a large capacitor, And so when you're working on a power supply, you have to be very careful. You want to make sure you discharge all the capacitors before actually doing any kind of work disconnecting them or something, or you could get a very serious injury and shock. All right, so capacitors, they don't like changes in voltage. Okay, so they, you see the equation up here, you see that the voltage is equal to how much charge you put on it. But as we already said, charge takes time, right? But to move charge, that's a current, and it takes time to move charge. So the voltage on a capacitor will not change immediately. It takes a while to change. But the current can change. You can have very large spikes in current. And so your current will change as needed to satisfy Kirchhoff's current law. Right? Remember, we always have to satisfy Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law. Okay, but with a capacitor, Ohm's law doesn't really apply because there's no resistance here. Ohm's law is about, the voltage is equal to the current times the resistance. But with a capacitor, we don't actually have any resistance, and so Ohm's law doesn't quite apply to the capacitor. But Kirchhoff's voltage and current laws are always going to have to apply inside of a circuit. All right, now capacitors may or may not have a polarity. Most capacitors actually do not. If you look actually at this bottom capacitor here, this one is probably made out of a mylar dielectric, and there's ceramic dielectrics and paper dielectrics and all kinds of different dielectrics, and most of them actually do not require a polarity. However, there is one type of capacitor called a dielectric, called an electrolytic capacitor, where the dielectric actually contains like a moist paste sort of material in it. And these types of capacitors are the type of large capacitors that we would often find inside of a power supply. And these have a very definite polarity on them. So if we look at this, capacitor right here, you see that this one terminal right here is being marked as negative. So that's showing you that it has a negative and therefore a positive. So this applies to a DC. If you're wiring this up into a DC circuit, you need to make sure that the DC side, that the negative side of the capacitor is wired to, it doesn't actually have to be ground, but to the lower potential within the circuit, so that you have the polarity across these connectors correctly. All right, now inductors are made of a long piece of wire wrapped around a magnetic core. Now, sometimes that magnetic core could actually be air, which isn't a great magnet, but it does work, especially for high frequency applications. But inductors are coils of wire wrapped around some sort of core material. They store energy inside of that magnetic core, so they are storing magnetic, they're storing the energy inside of the magnetic field. So capacitors store it inside of an electric field, inductors store it inside of a magnetic field. All right, the unit for inductance is henries. All right, and you can see the L down there. The symbol is L, but the unit is capital H for henries. And when you're purchasing an inductor, we don't care about voltage, we don't care about power, but we do care about the current, because we're going to be passing current flowing through this wire. And so if the wire is too small, then the wire could burn up and destroy the inductor. So when you're purchasing a inductor, you have to consider, of course, how many henries it is, but also how many amperes of current the wire can actually handle. All right, now the actual inductance is determined by the permeability of the core. This permeability, they're talking about how easy or how much magnetic energy we can store in the core. And the mu symbol that we also use for micro is used in this instance for the permeability of the core, which is the physical type. Soft iron is one of the most one of the best for an inductor. As I mentioned, you can use air, but air is not really all that magnetic. But you know, we do make certain inductors with a air core. We also have the length of the inductor and the area of the core. So in this case, the area represents the area of the core. And there's one extra value in here, which is in the number of turns. All right, and notice that the number of turns in the equation, it's the number of turns squared. So if you take an inductor and you use 1 turn of the wire, and let's say that gave you 1 Henry. Okay, so you had 1 turn, 1 squared is 1, right? And so that would give you 1 Henry. So if you have everything else the same, but you make 2 turns, now you got 2 turns squared, that's 4 Henries. All right, so by doubling the number of turns, you actually quadruple the inductance of that inductor. All right, so the inductive behavior, basically current, as we pass current through the inductor. Now current does flow through an inductor. Remember, current does not flow through a capacitor. It does not flow through the the dielectric of the capacitor, because that's an insulator. But current does flow through the inductor because it's just a piece of wire. But as current starts flowing, it builds up that energy within that magnetic core. So the inductor, if it's not charged, it actually behaves almost like an open circuit, because as current starts flowing, we're taking a lot of that current and storing it inside that magnetic field. Now, the magnetic field is going to get saturated. It's going to get filled up as much as it can go, and then that'll be it. So when once the magnetic core has been saturated and it's full, then the inductor, it looks like a piece of wire, and so it's just a short circuit as far as the inductance goes. Right? So inside of a DC circuit, after the inductor has been charged, after enough time that the inductor has been charged, it acts like a short circuit. Where when we charge up a capacitor, it looked like an open circuit. Now inductors do not like changes in current, okay, because as the current changes, what you're doing is you're affecting that magnetic field. And so inductors don't like changes in current. However, the voltage across an inductor can change in the blink of an eye. So if you open up a switch or something to try to interrupt the current, the voltage across that switch or across the inductor will change immediately in response to that. But remember that Kirchhoff's voltage law will always apply. At any time, Kirchhoff's voltage law is going to apply to your circuit, and Kirchhoff's current law, of course, will also apply to your current. All right, so let's take a look at wiring up these elements in series. So we've already talked about the resistors. We know that if we have two resistors in series, they're going to add together. If we take two inductors and put them in series, they're going to add together just like resistors, exactly the same. However, capacitors, capacitors in series are going to decrease. But now the interesting thing is if you look at this shape of this capacitor equation down here, when these things, when capacitors are in series, the total effective capacitance is 1 over the first capacitor plus 1 over the second capacitor, and so on. And we've seen this form of this same equation with parallel resistances, which we'll actually see over here. So if we look at a parallel connection, we see that resistors in parallel, right, the resistance decreases as you have 1 over R1 plus 1 over R2 plus 1 over R3 and so on. So inductors, if they're in parallel, they act pretty much like resistors. So as far as combining inductances, they add in parallel with the reciprocal notation just like the resistors did. Right? So, but capacitors, on the other hand, if you think about the capacitors, have these parallel plates, and so if you put two capacitors in parallel, you're basically doubling the amount of plate that you have, and therefore your capacitors just simply add together. All right, so the form, notice the form of these equations doesn't change, whether it's resistor, inductive, or capacitor. So the only thing you have to remember is that the inductors have the same equation as resistors for parallel, but capacitors have the opposite. All right, so we really don't have any new equations to memorize, just to keep track of which are which. All right, so here are the circuit symbols for a capacitor. We have basically two plates. Sometimes it'll be curved. Sometimes the curve kind of indicates a electrolytic, but usually if that's the case, it'll also have like the plus sign as the middle one shows. They may also have one with like an arrow drawn through it, which simply indicates that it's variable. The inductor, its symbol is L. Remember, the units are henries, H, but the symbol is L. And inductors are made up of wire, so they always also contain some resistance. Okay, so we like to model, if you're worried about the resistance inside the inductor, which you normally do have to take that into account. But if you have to take that into account, remember that that resistance is actually in series, because remember, the inductor is just a big long wire, but we like to model that by breaking it out and having a resistance in series with the inductance, so that when we just look at an inductor, we assume it's a perfect ideal inductor. Now, I don't have one on the slide here, but we could have an inductor with an arrow through it indicating that it is variable, that you can adjust the inductance. One common way of doing this, like in radios or whatever, would be to have that magnetic core with threads on it, and you can kind of move it in and out of the wires, of the wraps of the wire, by threading it through, so you have more or less of the core in there, and that would make it variable. All right, so here's just a combination. At the top here we have a simple series parallel resistor circuit. I have first resistor with 12 ohm 12 ohms resistance, and the other two resistors are in parallel and they're 20 ohms each. So the first thing we would do would be to combine the two parallel resistors, and I called that R23, and of course that's only going to be 10 ohms. But now we have this R23 in series with R1, so the total resulting is 22 ohms. So when we look at the inductance of a circuit that's the same type of circuit, we combine them the same way. So we combine the two parallel inductors, 20 henries each would model down to one inductor of 10 henries, and then that is in series with L1, and so the total again would be 22, but the units of course are henries because we're talking inductors. But if we look at the capacitors here, capacitors add in parallel. So when you look at C2 and C3 that are 20 farads each, we combine those into a capacitor of 40 farads. And then those now are in series with the C1, but when they combine in series, it's like resistors were in parallel, and so we end up with something less than 12. All right, so we end up with something less than 12, and the actual value down to 3 significant digits is 9.23 farads. All right, so that's how we combine capacitors and inductors in series and parallel.